Hello? We're good? Awesome. Okay. Right. So has anyone programmed a video game before that involved vectors? Yeah, there's like a couple of people who've used some vectors for legit, for real. So just some ideas that I had for things that we could program in this class that would get you really, really, really knowledgeable about the material. So things that would use the material from this course and would teach you a lot about programming and teach you a lot about vector calculus. The first thing that comes to mind is what's called an n-body simulator. So what an n-body simulator does is it simulates the action of gravity on n points. Okay, so an ideal n-body simulator, you'd be able to plug in the weights of the 9 planets. Does Pluto count or not count? I don't. Anyway, you could plug in the actual weights of our planets, and it would simulate our solar system, and that'd be really cool. So that's an idea if you want to know a little bit about vectors and a little bit about calculus to try and program one of these. The other thing that came to mind as something that would be very relevant to the course and would get you using the tools from this course what's called a gradient descent optimizer. So if you guys have done any data science, you might have heard of gradient, oh sorry, whoops. A gradient descent optimizer. So how do these things work? You've got some function, and they give you the min and max of those functions by following the gradient of the function. So this by following the path of steepest growth. Okay, so those are just a couple ideas of programming projects that would really solidify the ideas in this course. And if you've done any video game programming, another thing that might be a very useful thing would be a a 3D graphics engine. So, we've only got 4 months, so we can't do anything super sophisticated, but these are sort of 3 ideas for programming projects. If you really like programming, these ideas would really help solidify the things in the course. Any questions about those 3? I was just looking at the survey results, and I figured there's a lot of programmers, so I thought I'd give you some programming ideas related to the course. Okay. So let's leave those there for the curious. And if we're going to do a 3D graphics engine, we should know a little bit about lines and planes in space. So let's talk about lines and planes in space. Okay, so now we're coming back to the regular scheduled curriculum. Okay, so take a moment and either look up from last lecture or try and recall this thing that we call the parametric equation of a line. So try and write something down, see if you can remember it. So in the last lecture, we were calling the following the parametric equation of a line. Okay, so what does this mean? What are the various parts of this? So P is our initial point. D is the direction that the line is traveling in. And T is our parameter. Okay, so what does this look like? We label our axes with this guy always being the x-axis. So the parametric equation of a line tells us that we go to some initial point P, and then we want to define this line here. So we pick a direction D, and we add all stretched copies of that D. So that will go along this whole line here. So this is our parametric equation of a line. Okay, so let's use this to do something. Okay, so let's find the parametric equation of a line passing through these 2 points. How should I start this off? Yeah, sure. Back here. Okay, which one do you want to use as the initial point? 1, 2. Okay, sure. So this is going to be our initial point. Okay, so we pick okay, and we could pick 1, 2, 3, or 4, 5, 6. Both are fine. All right, now that I've got my initial point, what do I do? Yeah, sure.
Make it the origin?
Okay, sort of. So we've got this guy here, and then we want that corresponds to t equals 0, which is kind of the origin, right? But so when t equals 0, this guy will go away. So we need to pick a direction vector, right? How do we pick the direction vector? Subtract them. Yeah, good. So okay, so we're going to say the direction vector is 4, 5, 6, 1, 2, 3. Okay, so we get 3, 3, 3, and thus the line is like that. So we plug everything back into our formula. Okay. Any questions about that solution? Thoughts? Okay, yeah? Yeah, if we wanted to, we could do that. So what the point that was just raised was, can we reduce 3, 3, 3 to 1, 1, 1? Right? It's kind of a nicer formula somehow. What does that correspond? So I'm just going to just write that those are equal. Okay, but I've changed my variable now. I've gone from s to t. What does that correspond to geometrically? Right? So what does that mean geometrically? It means I'm switching from three times a direction vector to just the direction vector. Those are always going to stay in the same direction, right? So I could switch this 3, 3, 3 to 5, 5, 5, or anything that stays in the same direction. Okay, so that's one alternative solution. Very good. So we've talked a little bit about lines. Okay. Okay, so now I want to introduce the parametric equation for a plane. Okay, so let's start off with that same idea. We're going to take our initial point, and what should we add to this initial point to get a plane now? Yeah?
Two non-zero, non-parallel vectors.
Yeah, that's very specific and very good. Oops. Okay, so we're going to add two non-parallel, non-zero vectors. Right? If we added so let's imagine that the red pen and the blue pen are our vectors. If we're adding scaled copies of these, we'll trace out a whole plane here, right? My hand will be where the plane is. But if these guys were parallel, right? If the two vectors that we added were end to end, then we'd trace out this line. Okay? So we need that the two vectors are not parallel so that we get that surface that we want. Okay, And if one of them was 0, right, if the blue one was 0, then we just trace out a line again. So we want non-zero and non-parallel. OK, so what does that look like? OK, so far very similar picture to a line. We go to our initial point P. And then we go in the directions D1 and D2. And then that gives us that whole plane, okay? That whole infinite plane. Okay, good. And now we can kind of imagine if we want the parametric equation for a k-dimensional thing, we should add k non-zero, non-parallel vectors. OK, so very good. OK, so let's find the equation for a plane containing some things. Okay, so let's find the equation of the plane containing these guys. Just a little bit of a minor notational note. When I'm writing really fast, I don't write the commas. Assume the commas are there. OK, good. So let's follow the same kind of idea that we did before. I'm going to pick an initial point to lie on our plane. I'm going to be a little bit weird and pick this guy. OK, so I'll pick the second one as our initial point. And now we have to find the two direction vectors that we go in. OK, so we've got our initial point. One of the direction vectors will be from our initial point to here. OK, so I do that subtraction. OK. Now my second direction vector will be from the initial point to here. So I get like this. OK, so there's our two direction vectors. Okay, so we put stretched copies of our two direction vectors, and we add that to our initial point. Okay, any questions or thoughts about that setup? Okay, so that's how we write down at least parametric equations for lines and planes. It's kind of a similar procedure. We pick an initial point, and then we stretch, or we add stretched vectors to that initial point. Okay, good. Now there's another form of a plane that's going to be very helpful for us. Okay, so yeah, so let's erase this first. Okay, so far we've thought about planes in the following way. We take two non-parallel non-zero vectors and we span them like this. And that gives us the folder which represents the plane. Another way of thinking about a plane is as the set of guys orthogonal to a given vector. Right? So the folder is the plane of points that's orthogonal to the green pen. Right? We can see that there's a 90-degree angle there. So the plane represents the set of vectors orthogonal to the green vector. So let's try and write that down as a formula. Okay, so this is often referred to as the normal form of a plane. Okay, so we can imagine the plane as being the set of guys that are orthogonal to a particular thing. Okay, so one plane that we have is the xy plane, and we want to write that in normal form. Okay, so what's something that's orthogonal to the xy plane? What's a vector that's orthogonal to everything in the xy plane? Z, yes, yes. Please just shout things out, or murmur things out if you're the kind of soft-spoken type. So, observe. Okay, so the z-axis is orthogonal. So we've got a picture that kind of looks like this. Here's our xy plane. Here's the z-axis. And then there's a 90-degree angle there. So we can say the following thing. Okay, the xy plane is the set of points that have dot product 0 with something on the z-axis. Okay? We could put any number we wanted here, sorry, any non-zero number we wanted here, because it would still give us the z-axis. Okay, very good. So that's a plane in normal form. Okay. Okay, so one comment about this definition okay. Oh yes, I tend to write pi for planes. Okay, so it's not the number pi, it's just a handy letter for denoting a plane. So if a plane is defined by this, right? So if it's defined by the set of vectors orthogonal to n, then the 0 vector is always in our plane, right? So if we think of the plane as being the set of guys orthogonal to the vector n, then v equals 0 has to be in there, because right? Because the 0 vector is always going to satisfy this. Okay, but we want more planes than just planes that go through the origin, right? We want planes that miss the origin. Okay. Is everyone okay with the reasoning here? Is that all right? Yeah? If I think of the 0 vector as a bunch of zeros, whatever I dot that with will give me 0. Okay, so now we can say the definition of normal form. Okay, the normal form of a plane pi is the following thing. So to get around this issue that we always contain 0, we subtract something off. Okay, so here so p is a point, and n is the guy that we call the normal of pi. So we're going to say this. Okay, so that allows us things that don't contain the origin. Okay, so let's try some Let's try and express something in normal form. Okay. So, so take maybe a minute, 2 minutes, and try and get started on this. Try and identify the difficulties with this problem. Write some stuff down, and then we'll go through how to do this in a moment. So what was the difficulty with this question? What's the hard part? Where did people get stuck? Or did people get stuck? Okay, so what do we need? Well, to do normal form, we need a point and we need a normal. What do we have? Louder, louder, be bold.
3 points.
We have 3 points. Okay, so we've got more than enough points, right? What do we lack? Yeah, okay, one guy's like, normal. Awesome. So we lack a normal. So we've got okay, so we don't have the normal vector. How could we get one? And don't say cross product. If you know cross product, don't say that. How could we get a normal? Yeah, sure. Uh-huh. Yeah, okay, so let's make a normal. We don't have one, let's make one. Okay, so we're going to take our 2 direction vectors. We can pick any one of these as our initial guy. So let's pick the first one. Okay, so we've got our 2 direction vectors. Good. Okay, so to make the normal, we're going to find something orthogonal to both of these. Okay, we need to be orthogonal to both the direction vectors because then we'll be orthogonal to everything in the plane. So assume that this is our normal. Okay, if n dot the first direction vector is 0, then that tells us negative x plus y. Okay, so now we know some stuff about our vectors, right? We know some facts about x, y, and z. So what we have to do is we have to pick x, y, and z that make this normal vector. Okay. So how should we pick them? How should we pick x, y, and z? Yeah, over here, yeah. Sorry, a bit louder. Oh, okay, yeah, let's go with that. So I'm gonna do just one more step there. I'm gonna move the x over to the other side. X equals y. And then x equals z. Oh, look, now x equals y equals z. That's pretty handy. Okay, so now we have to pick a non-zero normal vector. So we're just going to pick a number. What's your favorite number? 2? 6? 1?
0.
No, let's not pick that. Okay. Right, we're going to pick a non-zero number. Yes, good. You're sneaky. I like you. Okay, I heard 1, and I'm going to stick with that. So okay, and I just want to say a little bit about what this choice means. So coming back to our highly scientific apparatus, here's our plane, right? And we've got this normal vector, and that's fine, but any stretch of that normal vector will still work, right? So if we take that normal vector and multiply it by 2, we'll remain normal to the plane, right? So if we have a normal vector, we can multiply it by any non-zero number, and we'll stay normal. So we picked 1 here, but we could pick any non-zero number. We just pick 1, 1, 1 because it looks really nice. Yeah. Yeah, we could scale it. Yeah. Good. So our final normal form is okay. I erased the initial setup, but what do? We do v minus one of the points. And then we take our dot product with our normal vector. Okay. Good. Any questions there or thoughts there? Yeah, sure. How do I differentiate between the origin and a point? Ah, a coordinate and a vector. Right. So we're gonna kind of like we're gonna be a little bit sloppy with that. We're gonna go back and forth. So that's a really interesting point. How does it look like? So we can think of a point in three-dimensional space, like we could think of 1, 2, 3, right? And that's the coordinates of the points, right? That's 1, 2, 3. But we're often going to flip back and forth, thinking of this as the vector from the origin. Okay? A little bit later on in the course, we're going to talk about vectors more in depth, but for the next like 2 or 3 weeks, we're going to just switch between coordinates and coordinates and vectors kind of indiscriminately. Okay. All right. Are there more questions or thoughts? So I'd like to give everyone a 10-minute break to get up, stretch their legs, do a little bit of yoga if that's your thing. Okay. Live. Okay. Welcome back, folks. So the plan for the rest of the lecture is as follows. So I want to do a couple more examples that are very similar to stuff in the homework. So I want to do a couple other examples, and then I'll do a little bit of a summary of concepts that we talked about this week. And then I want to leave you guys to look at the homework questions and the midterm question. So so if you remember from the blog, there were 2 midterm questions. And I kind of hope that by the end of the lecture today, you'll have all the tools that we need to do those questions. So I'll talk for about maybe 20 more minutes, and then we'll just work on problems and discuss stuff. Okay. Or sorry, talk for 20 minutes, summary, and then work on problems. Okay, cool. So we've talked about lines, we've talked about planes. So let's see some other stuff that we can do with lines. Okay. So one of the things that we want to do with lines is we want to determine whether they intersect or not, how they behave in space. So if we think of these guys as our direction vectors of lines, several things can happen in space. One of the things can happen is that the lines intersect at a point. That's fine. They can touch. They can be parallel and never touch. They can be something in three-dimensional space that's called skew. So 2 lines are skew if they're not parallel but they never touch. Okay? Or they can just be the same line. Right? They can go completely in the same direction. Okay, so let's write those down. Two lines can be what we call coincident. That means they are the same line. Okay. They can intersect at a point, right? So they can just run into each other. Or they can be parallel. Okay, so all 3 of these things can happen in 2 dimensions as well, right? We can have coincident lines, we can intersect at a point, or we can be parallel. So these are all 2-dimensional phenomena. Okay, that's fine. But in 3D, we have this extra option. 2 lines can be skew. Okay, so they can be non-parallel and never intersect. So these are just some terminology about how things can happen in 3D. Okay, so let's try and figure out if some lines intersect. Okay, so let's determine whether these lines intersect or not. Okay, how should we set this up? What should be our first step? Right, to see if the lines run into each other, yeah?
You put them in terms of x, y, and z.
Yeah, we can just write everything in terms of x, y, and z. Good. So okay, so what does that look like? Okay, so we group everything, and now we've got x, y, z is equal to this stuff. Okay, now we've got some other stuff that x, y, z would be equal to. So how do we determine whether these guys intersect or not? Right, we want to see if we can get the same output for x, y, z from both equations. Right, we want to see if we can get this guy to equal to this guy. Right, the outputs for t to equal to the outputs for s. Okay, so we're going to set the two equations to be equal and solve from there. Okay, so now we're looking for values of s and t that make this happen. So we can move everything. We can move all the constants to one side and all the variables to the other side. And what do we get then? So we're going to move all the constants to the right-hand side and all the variables to the left-hand side. Okay, so now we get something that looks like this. Okay, and now this is a linear system, right? We've got 3 equations, 2 unknowns. We hope that this thing has a solution. Okay, so when we've got a linear system like this, we can write it as an augmented matrix. Okay, so what I did was I just ignored the variables and I just wrote their coefficients. So this negative s turns into a negative 1. This 6t turns into a 6. Are people okay with that? Are people definitely not okay with that? Pretty neutral crowd, tough crowd. Okay, that's fine. Okay, good. So we're here now. Let's do some linear algebra to get this to a nice simple form where we can read off our solutions. So I have a particular notation for writing a lot of the row operations. So I'll show you what that notation is. Okay, so what does this mean? This means row 1 and row 2 switch. Okay, so R1 means row 1, R2 means row 2. Like this. Okay, now we've got a 1 here, and that's a good place to have a 1 because now we can subtract it from these rows and clear some stuff up. Okay, so when I write something like this, I mean row 2 minus 3 copies of row 1. Why do I choose 3? Because I want to get rid of this 3 here. Okay, cool. Now I want to get rid of this, this 6 here. So what should I write for my row operation to get rid of the 6? Yeah?
Row 3 minus 6 row 1.
Minus 6 row 1? Sweet. Yeah, good. So there's my row operation that will get rid of this dude. Okay, and then our last fundamental row operation is multiplying by a number. So here I've got a 5. I want to get rid of that 5. So I write 1/5 of row 3. Okay. Good. And now I've got stuff above this 1, so I want to get rid of it. Oh, just one thing I should say about this notation. The row getting acted on always comes first. Okay, so row 2 minus 3 copies. Row 1 plus a copy. Okay, so the guy receiving the action always comes first. Okay. Very good. And then our last move is to switch those 2 rows. Okay. Good. So we've used some tools from linear algebra. We've got our variable t and our variable s. And what do we get? Okay, so the column corresponding to s, right, that's this column here, s is equal to 0, and t is equal to 1. Okay, so we've got the values that make these two things equal. Good. Oh, one sec. Let's have a look. Yes, by George, you're right. Okay, sorry, scratch that. So the first column here is t, and the second column here is s. So this tells us that t is equal to 0, and s is equal to 1. Good. For the people who just said, shouldn't it be the other way? You're doing good work. Okay, awesome. So we've got those values. Okay, so one of the very nicest things about math class is that you can check your work. Okay, I used to study philosophy, and it was really hard to check your answers in philosophy. You'd ask God, is this how it goes? Okay, never mind, weird joke. So we can check our answers by putting in these numbers that we got. And if we did everything correctly, then the numbers will agree. Okay, so when we put in t equals 0, we get 2, negative 1, 6. Oh, this doesn't look good. We're way off. 2, negative 1, 1. Uh-oh. Okay, so we have a problem somewhere.
It's 2 negative 1. Yeah, 1. It's 2 negative 1, 1 for the first one.
2, negative 1, 1. Oh, there we go. Oh, thank goodness. Phew. Oh, wow. Phew. Okay. See, it's very good to check your work. Right. Okay. Yes. Was there a 6? Did I just make up this? Yeah, the 6 is here. Right, okay, the 6 is here. Okay, good. Any questions or thoughts about that procedure? So what do? We take the lines, we make a linear system out of it, we solve the linear system, we find out where they are. So these guys agree, and that's awesome. Good. Okay. Good. So we've talked about two lines meeting. Now let's talk about two plane, or a line meeting a plane. Okay, so we want to find out where line meets plane. By the way, this plane here is in an alternative way of writing normal form. So we can think of this equation as really saying the following thing. Okay. So this equation is sort of a normal form representation. Okay. So we've got the line, we've got the plane. Let's find out where they meet. Okay, good. So what should we do to determine where they meet? How can we figure out where the line meets the plane? Any guesses or thoughts? Yeah, back here. Yeah, let's do that. Let's use so we've got the parametric equation here. Let's find the x, y, z and plug them in. Yeah. Okay, so we'll find x, y, and z for the line and then plug those in. Okay, so there's our parametric equation. Now let's add the things and see what we get. Okay, so that tells us the location of x, y, z. Good. And now we're going to substitute those x, y, and z into our plane. Okay. Okay, so if these guys meet somewhere, then they'll meet where those coordinates of the line take on these values here. So let's put those in. Whoops. Okay, so they'll meet where t satisfies this equation. So we get 2 plus t plus 2 plus 2t equals 0. So we get 3t is negative 4. So t is negative 4/3. Okay, thus the line and plane meet where t is negative 4/3. So that would be like this. Okay, so they meet there. Any questions about that solution? Right, so once we get the coordinates of the line, we can put them into the equation for the plane and see if they match. Okay, very good. So that's what I wanted to say in terms of new examples and stuff. Now I'd like to take a couple minutes, summarize, and then ask you guys how the homework's going. So we've got this stuff. Okay. Okay, so what did we talk about this week so far? What were kind of the big ideas of last lecture? Dot product, right, totally. Okay, yeah, dot product, what else? Yep.
Orthogonal and parallel vectors.
Yeah, orthogonal. Oh yeah, and it's fine to look at your notes. If you, in answering the question, what did we cover, it's fine to look at your notes. Parallel. Okay, what else? What else have we seen so far? Yep.
Length of a vector.
Yeah, length. We didn't calculate too many lengths, but we saw them. Yep. Yeah, the angle, right? So this is this kind of key formula. Oh yes, some person asked if we could do more proofs. I know, right? Don't stone that person. They were well-intentioned. But there's not going to be too many proofs in this class. I think that most people kind of are like, proofs. So there'll be a couple sort of like bonus questions that are proofy. But there's one proofy question in the homework, and we need to know about angles to do it. So okay, so this is our definition for the angle between two vectors. Okay, yeah, so we saw angle between vectors. What else did we see? Any other? Yes, parametric equation of a line, right. Okay, good. Any other things that we saw this week? How about today? Any new stuff today? Yeah. Yeah, planes. Okay, we saw the parametric equation of a plane. Any other things? Yep. Yeah, good. Yeah, intersections. You know what? We need more space. Okay. Okay. Any other things? Yeah.
Normal equation of a plane?
Yeah, right. Normal form. Okay, wicked. Yeah? Yeah, so we... So we only saw an example of intersect, but there are other types. We've got coincident. We've got these guys. We'll deal more with the other types. I think that's a pretty accurate summary of what we did. Is there anything else that comes to mind? Okay, so that's kind of what we've seen so far. So I want to do this kind of at the end of every Thursday lecture, sort of to get a feel for what we did. Yeah. Oh, a thought I had. All right, so if you take PDF notes on a tablet or something, it's helpful to have more notes. The more notes, the better. So I'm going to be posting notes on Fridays. I find that if I post notes on Mondays, no one comes to class. I don't blame them. So if you take PDF notes and you feel like sharing them, please email them to me. You'll be like a course hero. You can remain an anonymous here if you want. But yeah, if you're taking PDF notes, please email them. Okay, yes? Sure, yeah, one note counts. Yeah. If it outputs a PDF, I'm fine. Okay, so did anyone print off that sheet, the syllabus sheet? Yeah, you did? Yay! Gotcha. Okay. I didn't. Who didn't print it off? Okay, guys, please print it off soon, because the homework really matters. Are there any questions that came up from the homework? Did anyone try something and want to ask about it? Any thoughts, attempted questions? I can see everyone is preparing to flee. That's okay. So I want to reserve this time for talking about homework questions after the summary. Are there any homework questions? Yes? The plan is to keep it this way, yeah. The plan is to do summary, homework discussion, office hours. Right, a couple of people booked office hours. So I want to meet in IC 467. Okay. All right. Thanks a lot for coming in, folks. Please print that sheet ASAP.